Hey everybody, my name is Paul, W1VLF. Welcome back to the lab, and as you can see, the Group W bench is just covered with crap. Let me grab a hold of the camera here real quick and I'll show you what it is that's going on. Alright, so what we have on the lab is, here is, we have a laser. This is about a 5 milliwatt green laser. We have a power supply and a fan. Wonder what that's for. And then we have this little skinny piece of aluminum tubing with a detector in the end. And the detector feeds a piece of wire which feeds into the audio amplifier here. Okay. And it's an optical detector. And what it's going to do is change voltage out of that detector, and I'll do this in a PowerPoint over at the desk so it's a little bit clearer, but I just wanted to show you what I have on the desk here first. So I'll just turn the laser on. Okay, it's just a green laser. I don't know how great that picks it up, but the output of it is connected right to that amplifier, and of course the only thing you hear when I first turn the laser on, just a little click. Nothing else, because this is lighting up the LED, the photodiode in there, and it's essentially producing a little bit of direct current, just as this would. This is a solar panel cell here, and essentially what you have is in the back of this is a tiny little solar panel sitting inside a metal can called a photodiode. They're available everywhere in the world on eBay for 50 cents, $1 a piece, something like that. Mine are quite old because I've had them for a long time. This is kind of an experiment that I did a long time ago, and I used them for that. Anyhow, so this is a green laser. I don't know how close I can get, and this will still focus. But so what's the idea here is? What's the idea? The idea is whenever you cross paths, whenever this DC volt, this light, the light from the laser beam changes in amplitude, and in this case, no light to light, no light to light, you hear sort of a click. You hear the voltage going from 0 to whatever voltage is being generated by that photodiode. Okay, so I put a little piece of green, piece of diffuser paper on the front so you could see it. So there, the laser, turn the laser on and off with my hand. Oh, that's really exciting, Paul. Okay, so what we're going to do now is I'm going to block the laser. It's still on. I wish the light wouldn't go out in this camera all the time. I guess they need to do that. Okay, so the laser's still on, but now it's being interfered with. You don't see anything. You don't see anything because one of the blades is in the way. So if I move a blade, the light comes on. The blade is blocking. It's not blocking. So now I'm going to turn on this power supply. You can see how that moves, right? I'm going to turn on the power supply. I'm getting to something, real, guys, here. Honest to God. Let me walk around the back. So here's the power supply. We'll turn that on and you take a listen. Okay. You can see that turning on and off. All right, and I'll let it just discharge. So why did I do all that? Well, I did all that because what we're going to do here is we're going to put the laser out in the barn. We're going to point it back towards the house, and it's not going to be a green laser. It's going to be a red laser, and it's a very low power 1 milliwatt laser. So the first, I guess I should have started this by saying, please don't ever look into a laser beam. You can do instantaneous damage to your eyes. These are low power lasers, granted, but the eye response can sometimes be slow and you could do damage to your retina. So with that in mind, don't ever look into a laser beam, okay? It's just not a smart thing to do. So here in the barn, we have a 1 milliwatt laser. And in the house, looking out through that window, we have the detector. And so what happens is, by the time the laser reaches the house, it makes a 1-inch dot. Okay, whoop. A 1-inch dot, maybe it's a 2-inch dot on that piece of paper. And I think I explained to you about this in another portion of the video, or I will, where the laser was drifting back and forth. Anyhow, that's the size of the laser beam when it hits the house. Okay? Now, the same thing happens here, where when there's no light, there's no sound. Right? Turn it back on for just a second. Okay. So what happens is, when you look out in the backyard, there's mosquitoes, bugs, moths, birds, all sorts of things that fly through this beam. And you can actually hear the modulated tone as their wings flap through the beam. So instead of it being a fan that's cutting the beam, making it go on and off to the detector, it is the wings of moths or flies or mosquitoes, all sorts of different bugs. So I'll put a couple of them. And, the other thing is, you can tell the relative speed of the wing beats by the frequency that you're hearing as you interrupt that light. Like a small mosquito might be, a moth might have wings that beat at a couple of hundred hertz per second, and a mosquito might be significantly higher. And I'll demonstrate some of those. And then at the end of this video, what I'm going to do is I'm going to put up like 5 minutes of time, which is condensed. What I did was let this whole operation run overnight, and then I deleted the silence and only left 1 second. So every 1 second you'll hear some sort of a blip or a noise that was generated by a mosquito or moth or whatever. And you'll be able to hear those. This is really crazy, isn't it? Sometimes I don't understand what it is I'm doing myself. Anyhow, you'll be able to hear those. So nothing really radio related, but I just thought it was kind of cool. So the other thing here's another thing. In the wintertime, when snowflakes come down, they have a very distinctive sound because they make and break in the beam of light coming in. And also when it rains, there's kind of a distinctive sound. So anyway, let me get on with a couple things here and let you hear what it sounds like, and we'll go from there. Okay, just a quick word of warning here. Never, ever, ever, ever look into a laser beam. It seems like it's very tempting. It seems like, you want to see what's going on in there. Even if the laser is off, there's a chance that something in your circuit might turn it on. Look at it like a gun barrel. You wouldn't look down the barrel of a gun. Don't look down the barrel of a laser either. Okay, so just quick things about things that go bump in the night. Really, really quickly here, we have the laser, which is that 1 milliwatt. 650 nanometers means it's red. The laser is just a constant light beam, no modulation at all. And then the detector, and as long as that light beam is constant, the detector will just put out DC. Won't put out any sound, just a DC like a solar panel. Here's my poor excuse for a fan down below. And when that laser is putting a constant output, the fan will chop it into on-off sections. On, off, on, off, on, off, on, off, on, off. And that's what you heard on the test setup on the Group W bench there. And here's the interrupted sound output from the light turning on and off. And there's only one more thing here I wanted to talk about. To give you an idea, from 150 feet away, there's a thing called laser divergence, and that means how fast does the beam spread? Well, it spreads, typically they're measured in milliradians, and this laser is a 1 milliradian laser. So what is a milliradian? It's 0.057 degrees. Okay, so not like 60 degrees like your HF beam, or 17 or 20 degrees like a 2-meter array might be, or even 1 or 2 degrees that a 10 gigahertz system might have with a dish. The laser divergence here is 0.057. So pointing that at the house and getting everything very, very stable was quite a feat to keep it not moving. The distance is 150 feet. Oh, and why the detector tube is a question some people might ask, right? Because you only want to see the light coming in directly into the detector diode. You don't want all this other light, because this is all junk, right? Everything that you're collecting here with this diode, if it were just open, everything you're collecting is noise except for the desired signal, which is that thin laser beam coming in. So the inside of this tube is painted black, and any stray light gets absorbed into the black and is dissipated. So that's about it for the PowerPoint. Just one more thing. I'm going to be showing different examples here of high and low frequencies that you hear from, different mosquitoes and bugs and things that are out there. But I'll let the whole, it's like 8 or 10 minutes run at the end of this of everything I gathered in my one overnight run that I did. The overnight run was actually 14 hours. But I used Audacity to knock all the silence off. So take a listen to that if you're interested, but I'll have some examples so you won't have to live through that, because it is going to be painful. All right, W1VLF, I'm out for the moment. Okay, so I tried this laser experiment from 2 locations. Alright, here's location 1 in the barn. I hope that's in focus. I can't really tell. Anyhow, that's the small laser up there, and the battery pack was connected to the 2 wires that you see there. And then that shot from inside the barn here, so it wouldn't get wet, up to the window there with the white piece of paper in it. And this turned out to be a really bad idea because at 150 feet away from the house, the change in movement right here in this beam, boy, this is really washed out, from day to night, moved it about 4 inches across the window. With a long lever arm like that and such a narrow beam angle, it was really amazing how much it moved. So I decided that wasn't any good, because halfway during the night, as the moisture level changed or the temperature changed, the beam would shift right out of where I was pointed. So I had to change it up. And here's the other one. See if we can get close to it. You can see it's still running. It's like a little red glow inside. And that one is pointed exactly the same location, but it's mounted to this steel beam here, or this steel beam, pointed up towards the window. Okay? And that worked out much better because it doesn't expand. It doesn't change with moisture. This is like a 4-inch, or excuse me, maybe 5-inch steel pole, and it was for a large C-band 12-foot solid satellite dish, so it holds very, very steady. And this is a piece of unistrut, so nothing moves. Very, very consistent signal. Right where I put it in the morning is where it is at night, is where it is the next day, over and over and over again. So anyway, I just wanted to let you see the path back. And you can see from both of these locations that we have a line of sight back to the house. All this is a piece of PVC pipe, small piece of PVC pipe, with the laser module mounted inside, and there, I went and moved it now. So I just touched it that much. That can change it off a foot on the other end. Anyway, I'll realign it back again tonight. But anyway, that's it. Just wanted to show you those locations. So a quick view from the inside of the house here, out to the barn. There's the barn where one laser was set up, and that pole out there is where the other laser set up. You can sort of see it glowing slightly. Anyhow, let me zoom back out. Put this piece of paper on the wall, on the window rather, and the detector was sitting around here, and that's where the laser was aimed, and it walked all the way over to here during the night, and then the next day walked back this way. And I'm going, what the heck is going on? There was nothing loose, but evidently something in the shed is moving slightly, and it wouldn't do it instantly. It would do it over the course of an evening. So anyway, just wanted to fill in that gap there. Now the other laser is pointed somewhere in the middle. It's tough to see right now, but it's stable and it doesn't move even half an inch. The size of the laser dot at this distance is actually roughly the size of those. It's 1.5 inches or so in diameter after 150 feet. Anyway, that's enough jibber jabbering. Back to real business.